Then, alrighty, here we go. Officially welcome everyone, or I should probably say welcome back. It's great to see lots of familiar faces again, also from outside the Department of Ergonomics here at the IFADO. We're always happy to have visitors. Yeah, we're finally relaunching our talk series again after a longer summer break. And I think I'm not exaggerating when I say that with Ngiam, we have an amazing speaker today to kick us off. Yeah, let me officially introduce today's guest. Will obtained his PhD in psychology from the University of Sydney in 2019, where he worked with Alex Hall-Comby and Patrick Goodborn. He then moved to the University of Chicago, where he's been working as a postdoctoral researcher with Ed Aw and Ed Vogel. And in his research, he mainly tries to understand how learning and experience changes how visual information is represented in memory. And he tries to use these insights to uncover the nature of capacity limits in working memory. But beyond his publication record, what is even more impressive to me is how much Will is really trying to move the field forward and develop a community here. He's been a really big advocate also for the open science movement. For instance, he's been a part of the steering committee of the Reproducibility T initiative, which tries to help early career research to establish a local community that fosters open and reproducible research. And he's also the editor-in-chief for the Journal of Reproducibility in Neuroscience. Yeah, this year I've already had the pleasure of serving together with Will on the organizing committee for the Working Memory Symposium, so I can really also say this from my own experience that Will really cares about the community and also especially empowering early career researchers. And also, last but not least, about improving science. And yeah, essentially, I guess this is also what we could say is what brings us here together today, because what we're going to hear about today is Will's most recent work that kind of led up to the development of a theory map that aims to integrate different views and models in the field of working memory. I do apologize for the lengthy introduction, but I felt like all of this was really worth acknowledging. Will, we're super excited to have you here today, and we really look forward to your talk. So please take it away whenever you're ready.
Oh, yeah. Thank you so much for that lovely introduction that I'm certainly undeserving of. Yeah, it's my honor to welcome everyone back from the summer break and to sort of start off the talk series again. I myself have watched many of the others who've recorded talks in this series. And so I'm hoping that I can simply add a little contribution to that collection. So today, I'll be chatting about rethinking attention in visual working memory and its researchers. I think the "and its researchers" is a little fun wrinkle here because in this talk, I'm not only going to be talking about how we might want to rethink how we think about visual working memory, but we might also need to rethink how the researchers are doing the research in visual working memory. So just to begin, I've got here 3 books that are in the sort of public that were recently written. A book on the left is a book called Stolen Focus by Johann Hari. And you can just see by the byline in the middle of that book why you can't pay attention and how to think deeply again. The reason I bring up this book is because I think it taps into this sort of feeling that everyone might be having at the moment, where there's a sort of collective uncertainty and about people's attention. So, for example, it feels like we're losing our ability to focus. We're losing our ability to pay attention and maintain our attention span, especially in this modern era of social media and digital media, where it feels like our attention is being captured by certain things. So there's a certain unease with that because it feels like we're not in control of our attention. The book in the middle is called Nobody's Fool. You might recognize the authors, Daniel Simons and Christopher Chabris. They were the authors of the infamous Invisible Gorilla study. So in that book, just recently published this year, they talk about when your attention is sort of captured and you become deceived. See, you can see by the byline why we get taken in and what we can do about it. So in that book, they talk about how people taking your intuitions and your familiarity and so on and so forth can lead you to being deceived, can lead you to believing in misinformation, for example. And also that taps into another sort of collective feeling where it's not only is our attention being captured and sort of not kind of being, not we're sort of losing our ability to focus, we're also getting more and more bombarded by noise and this like unable to sort of make out what is true and what is not. So yeah, it taps into that general feeling. And then this third book, Think Again by Adam Grant. This was published a while ago, but you can see from the byline for that book, the power of knowing what you don't know. And what's fun about this book is Adam Grant says to the public, oh, you should think like scientists. Scientists can sift through the uncertainty. However, while that is very much great advice for the public, I actually think scientists also need to heed that advice, that scientists should also think about what they don't know and to take the advice of thinking again. So my talk today is sort of trying to tap into this general feeling and examine this in the case of visual attention. So my talk has 3 sections. The first, I'll be asking what has got scientists' attention? The second is what is visual working memory? And in that, I'm going to share 2 empirical projects, which I've called Guess Bands and Conjunction Hall Report. And the third is how do we rethink visual working memory? So firstly, what has got scientists' attention? This is a graph that I pulled recently from arXiv, the preprint server. So on the x-axis, you've got time, and on the y-axis, you've got the number of submissions to this preprint server. And hopefully you can see straight away that the trend in this graph is that it's exponentially increasing. So I'm just using this as a proxy to suggest that we are publishing more and more and more over time. Of course, you might say, hey, this is just a preprint server, and maybe the popularity of this preprint server is increasing and increasing, which is great. I would love for preprint servers to be more used and more adopted over time. But I really do think this is indicative of the trend of scientific publishing and of producing more and more and more. And in fact, we do know how many papers are being published per year. So I'll let you take a moment, think about how many papers do you think scientific articles were published in, let's say, 2020. Hopefully you have a number in mind. Recent work by the National Science Board and National Science Foundation, and also has been replicated by SciMargo, estimates the number of articles published in just 2020 alone was 2.9 million articles. That's 2.9 million scientific articles. You can see on the figure on the right, if you follow the blue line at the top, that's the worldwide trend. You can see that number just gradually increasing and increasing, increasing. It looks like it's following some sort of exponential trend. And in fact, Pan et al. In 2016 did estimate this to be approximately increasing at 4% each year. In fact, I've also seen in other places estimates of increasing by 8 to 9% each year. So the number of papers we are producing across science are increasing and increasing and increasing. Here we have a recent work from Hansen et al. In 2023. This is a very recent preprint where in the black line here is the number of articles published, so exactly the line that I showed you earlier. However, the red dotted line is the number of PhDs awarded in OECD countries. I'm just using that as a proxy for the number of scientists that we're training. And you can see that the trend for that is that it is decreasing. And how this sort of, to me, raises a very big issue with our structures in science and academia. Essentially, with the growing number of papers and the lack of scientists to sort of coordinate, we're increasing the strain and the stress on scientists to read the papers, to review the papers, and to coordinate the papers. So I'm sure some of you have been feeling the weight of having or the weight of having to review a bunch of papers, or the weight of having to wait a long time for your paper to get reviewed at different journals. So there seems to be increasing strain, and that's just exponentially increasing. And also one problem that I see is that this will magnify an attention economy, because if we're producing more papers and there's less scientists across to try and coordinate, then we're going to have scientists competing for their work to be noticed and for their work to have an impact. So I think this is a structural problem that we need to address. In addition to the number of increasing papers being published, that might be a good thing, because maybe increasing papers, increasing production of science might mean more progress. However, there's another worrying trend, which is that there's a decline of negative results. So Finelli 2012 estimated the proportion of papers reporting a positive result or reporting a significant result was about 70% in 1990, and that had steadily increased to 90% by 2005. This figure comes from that paper, and you see across the three sciences, physical, biological, and social, you can see an increasing trend in positive results across all three domains. Of course, what pertinent to psychology is probably the social, or if you're in neuroscience, probably the biological, and you can see the trends are still increasing there. Now, we actually do have an estimate of the number of positive results in the psychology literature from a recent paper. So have in mind, what do you think that is? Okay, so it's recently been estimated in the psychology literature that the proportion of positive findings is approximately 95%. Now, I don't know about you, but if I were to do 20 studies, I don't think 19 of those would have significant results. I've certainly make more mistakes or find more null results than I would, is as indicated by the literature here. And so this is a worrying trend, because it feels like we're only seeing the positive results, and we're only seeing something that doesn't match the true reality. We have a biased picture of what is in the literature. So if that is the case, how can we be certain that we are understanding a system better, or understanding what we are researching better? So does more papers, mostly with positive findings, mean faster scientific progress? At this point in time, I say not really. And there's further problems with that I have yet to mention. One understated precursor to the reproducibility crisis in science and in psychological sciences is this sort of lack of coordinated theoretical development. Paul Mill in the 1970s had already criticized psychology in this way. He argued that there was an over-reliance on the hypothetico-deductive method, an overuse of the null hypothesis significance testing to make inferences. He argued that psychologists or experimental psychologists have been given a recipe, and they just use that recipe without thinking about what the inferences should be. And we also know that null hypothesis significance testing is problematic for other reasons, including questionable research practices. For example, p-hacking, harking, which is hypothesis after results known, and even data manipulation. So, yeah, and so in addition to that, with the null hypothesis significance testing thinking, we often assume this kind of setup. So this is a critique by Newell in the 1970s again, where he argued you can't play 20 questions with nature and win. I think scientists or psychologists recently have been thinking in terms of theory A versus theory B. So you can see here, we often see a setup where it says, these are the two possible theories to explain the result. I'm sure you've seen this in some of the papers that you've read recently, or some of the conferences, the talks. Scientists love to set up their paper by saying there's two possible explanations for this phenomena that I'm looking at. And so they'll say theory A leads to result A, or theory B leads to result B. And then they'll conduct the study and they'll show, oh, we did not see result A, or we did not find result A. So therefore theory A cannot be right, and therefore theory B must be right. Now, of course, hopefully you can see that there is a logical flaw in this here. You have not shown positive evidence for theory B at all. You've just simply shown that theory A is unlikely to be true based on your empirical result, because you haven't shown result A. But you do see in the literature, scientists often infer that their theory B must be correct when they don't see result A. the reality simply isn't like that. The reality is more like this picture that I've drawn. You'll see I have theory A and theory B in this cloud. The reason I did that is because these theories are usually quite nebulous. You can't really pin them down to be specific. And usually these theories are actually overlapping. They're not really separate in what they predict or in how they're defined. They're probably overlapping in some way, and they're probably not well defined, so they're kind of cloudy. Now, I've used these colored triangles to indicate what connection the theories have to the phenomena. And you can see both theory A and theory B will predict a certain range of empirical phenomena, but often they'll predict an overlapping set of phenomena. They'll predict the same set of results that we see. So even if we observe a specific empirical phenomena, we can't really tell apart these two theories, theory A or theory B, let's say. And also, we have in our empirical phenomena a bias, as I mentioned before, where we only see the positive findings. So we have underspecified theories that we can't really test incisively. We have underdetermined experiments. We don't have experiments that have direct connections to these theories. And we have an overfixation with these significant results. And so these three together lead us into a weird situation where we can't really make progress on our understanding or on our models and theories. So I mentioned earlier that we have a lack of coordinated theoretical development, and we over-rely on this null hypothesis significance testing, which is fraught with some potential false positive inflation with questionable research practices. But we also have underspecified theories and underdetermined experimental designs. We have theories and models that allow for ad hoc changes, so we can change our models to explain each of the results. We usually have straw man of competing models. So as I mentioned with theory A and theory B, you can make theory A look very, very weak. And so then you can show theory A doesn't seem to explain the empirical phenomena and make the flawed inference that theory B must explain the phenomena well or explain it better. And we also have fairly blunt instruments of measurement. We don't precisely detail a lot of the phenomena that are happening or a lot of the mechanisms that are happening. And also in our field, we have a tendency to overgeneralize our theory. I would argue that we are almost incentivized by our academic structures to try and overgeneralize our theories because it looks good to have a certain theory explain a whole host or a whole range of phenomenal empirical conditions, when we haven't actually done the work to show that the model generalizes or done the careful measurement to make sure our models are accurately capturing the phenomena that we're talking about. And to me, that's a bit of a sign of a lack of intellectual humility, a little lack of willingness to accept that we don't know certain things, and a willingness to accept there are uncertainties about the thing that we're researching. So I'm going to move on to the next section of my talk, which is applying that kind of thinking to what I observed in my research field, which is what is visual working memory? And so the first question to simply ask is, what is visual working memory? So a definition that you'll see often is something like this: the system responsible for maintaining visual information in a state of heightened accessibility for ongoing perception and cognition. I'm sure you've seen this in a bunch of papers and perhaps lectures or textbooks and so on and so forth on things like working memory. Now, I have a little gripe with this definition because I think this same definition could also describe a host of other things. For example, this same definition could also describe visual attention. What is attention if not maintaining a specific subset of information in a state of heightened accessibility that you use for ongoing perception and cognition, right? And so this definition of visual attention is nearly identical to this definition of visual working memory. And indeed, I think a lot of researchers are confused as to whether they're studying attention or working memory. And even though we call them different things and we silo ourselves into different labels, really we're measuring the same system. And so there should be more crosstalk across these two subdisciplines. You could also perhaps apply this definition to something like visual imagery. So even without perceptual input and trying to imagine something, you could argue that is maintaining visual information in a state of heightened accessibility. And perhaps even introspection, thinking about what you're thinking about, would also fit under this definition of maintaining information in a state of heightened accessibility. So this definition is sort of unspecific. And what the core questions that we really need to answer then is, what does it mean to maintain visual information? What details a state of heightened accessibility? What are the mechanisms that describe these processes? That's what we're trying to get to. Those are the core things that we're trying to understand with working memory. Indeed, this has been noticed by others. In a great paper by Nelson Cowan in 2017, the paper is called The Many Faces of Working Memory in Short-Term Storage. And I have a suspicion, Nelson, he's a distinguished professor in the working memory field. He's been around for a while. I have a suspicion that a lot of people go to Nelson and ask him about different phenomena and different models and ask him to try and make sense of everything. Like, what do you think about this? And what do you think about that? He writes a great sentence in his paper. It has become clearer to me that a major source of confusion is that researchers use different definitions of the malleable and useful concept of working memory. We do not seem to be converging on a common definition of the term. So it seems like everyone has different ideas and different perspectives on what working memory actually is. There is no common core that we're agreed upon. It's sort of everyone has their own idea. Again, this has also been raised by Bob Logie and others in a book chapter, Integrating Theories of Working Memory. This comes from a book, Working Memory, State of the Science, which was just published in late 2020, in case people have concerns that I'm sort of cherry picking our field and talking about the field from a decades-old long debate. I feel like this is fairly recent. In this book chapter, they write, we argue that many of these differences reflect different research questions, different levels of explanation, differences in how participants perform their assigned tasks in different laboratories, rather than fundamental theoretical adversity. So the point that they're making is, because we have different research questions or different focuses, we have different levels of explanation, we have different ways that participants do the similar tasks that we assign to different laboratories, leads us to a different, that's what leads us to differences in our understanding. And it's not actually fundamental theoretical differences. We're not actually disagreeing on fundamental theories, because we're just doing things in different ways. So taking the thinking from before and applying to this current situation in working memory, I want to ask, how do we make progress if there exists subtly different definitions due to different research questions, different methods, different measures, different contexts, different perspectives, different ideas? How do we generate theories that do explain the empirical phenomena that we're researching, especially when also theories or models try to explain all the possible empirical phenomena related to some ill-defined construct, here, working memory? And also, how do we make progress if models are too underspecified, such that the empirical tests cannot be definitive in picking out or choosing or comparing these models? And these models, in fact, may not even reflect any fundamental theoretical differences in the first place. So how do we make scientific progress in this case? Let me go through some of my empirical findings to sort of show you how I reached this approach or this understanding. The first project is guess bands, and this is work done with Josh Foster, Kirsten, and Ed. And honestly, a lot of the credit needs to go to Josh and Kirsten, who spurred this project, and I came in on the end. So firstly, let me explain the sort of debate that has been existing in the visual working memory literature for decades. I'm sure you've probably heard of it. It's slots versus resources. Let me explain the two sides. So first, we have slot models or item limit models. And the thinking behind that is that memory is contained to a few objects. And so there is no memory for the other objects beyond this capacity limit. You can only maintain a certain number of objects in memory. So if I were to show you clock faces like this, where your task was to remember the orientations of these clock faces, the item limit model would say you can only remember a subset of that information, let's say 3. And you can remember those with enough precision to report those angles at a later stage. So those 3 items are stored, but for the other items in the display, you have no memory for those items. So nothing for the other items. Of course, we can formalize these models. So in Zhang and Luck in 2008, they distinguish these two sets of responses. So on the left, you've got the normal distribution. So here, if you remember the item, you should report an angle very close to the presented angle. So your error should be close to 0. So that's why we have a normal distribution if you have a memory response. We call it a von Mises distribution because it's usually in a circular space. So a circular normal is also known as a von Mises distribution. However, if we don't have any memory for those items, it is assumed that people would guess and they would generate a uniform response. And if you have, that's because if you have no memory for the item, you should be completely random. So whatever presented angle, you just report some random angle. And so that should lead to a uniform distribution. I do have some gripes over the assumption whether people can be purely random and could generate a uniform distribution, but I'm going to leave that to decide because I don't have time for this talk. However, so if we have a combination of memory responses and a combination of guess responses, we add those two together, we'll have an error distribution that looks like the one on the right. I'm just going to call it sombrero hat because that's what it looks like. It's known as a mixture model in the field, but I'm going to give you a cue, a sombrero hat, so you can remember later on when I bring it up. Okay. So we have the competing model in the field, which is the flexible resource model or the variable precision model. Here, the thought is that memory is actually distributed across all the items. And this feels right because it matches our perceptual experience. We seem to be able to see everything. However, what's key here is that there's a flexible allocation of mnemonic resources. So if you add more resources to a specific item, let's say, you should have a more precise representation of that memory. So it'll be in higher fidelity. So back to these clock faces, what I've used to denote the amount of resources is the contrast. And so the more contrast you have for this representation, the better, or the more precise your memory for it, the more likely you'll have a precise response when you report the presented angle there. However, this changes across all the items, right? So you have some items with less contrast, less resources, so now it becomes more fuzzy. So the key point here is that all items are stored in memory, but that they're just at different levels of resources, so different levels of precision. We can formalize those models as well. So here you can see it's the same von Mises distribution from before. However, if you're more imprecise, those von Mises distributions get wider because your errors will get larger and larger. And so it would look like for all 6 items on the clock faces, you'll have 6 ranging von Mises with different precisions, let's say. And so if we add them all together, it looks like the error distribution on the right, which also looks like a sombrero hat. So hopefully you're starting to realize that this is an issue because the two things that we're trying to compare look so similar. They look very identical. And the main issue here is that an imprecise memory can mimic a random guess. We have to try and tell apart a flat line from a slightly bumpy line. And it might seem ridiculous, but the field was doing that for a brief moment in time. This is data from Kirsten Adam, one of the co-authors on this guess bands paper. And what she did was that clock face example that I showed you, but whole report. So you had to respond to all items on the display before moving on to the next trial. So we can see here at set size 1, you do have a central tendency, set size 2, central tendency for both responses, and so on and so forth. But the key here is at set size 6. While we notice a central tendency for the first 3 responses, for the last 3 responses, people were unsure whether there is a central tendency or whether there was a bump in the middle or whether it was truly flat. And it may seem ridiculous, but people argued for a long time whether there were imprecise memories in there or whether there were guesses. And in fact, Kirsten did the simulations and said you needed approximately 1 million noise-free samples to tell apart a very, very imprecise memory with a random distribution. And to be honest, no one's going to collect 1 million samples, 1 million noise-free samples from any participant. That's just sort of impossible. So we needed a solution to this. So our solution was to suppose that, a difference between these models is whether guessing exists. And what we needed is an experimental paradigm where guesses are clearly distinct from imprecise memories. So what we needed to do is have guesses produce a completely different distribution to a uniform distribution. So this was our experiment design. We did whole report of 6 orientations. So those clock faces I showed you earlier, and whole report, meaning participants had to report all items in the display before moving on to the next trial. Here we did experiment twice. Experiment 1, I had participants do 120 trials with the colored backgrounds and 80 trials without the backgrounds. And experiment 2, they did 160 trials with the quadrant backgrounds, but we rotated those backgrounds 45 degrees. You'll see why that's important later. Our thinking was simply by having these quadrant backgrounds in the display, participants will be biased to respond to the middle of these colored quadrants. Note that the colored quadrant is the same for all stimuli. It's the same for all clock faces. So it doesn't predict the angle that is in the display. There's no predictiveness from the quadrants to the angles. They're completely independent. So a response that is biased by these colored quadrants seems to be independent to any memory they have for the presented angle. So just to predict what we would observe, so on the left, I had shown you the von Mises distribution from earlier. I'm going to show you the data as scatter plots. So on the bottom row, on the x-axis is the presented angle, and on the y-axis is the reported angle. So if you do have a memory for something, you should report the presented angle. So that should form a diagonal on the scatter plot. The diagonal with some dispersion because there's some imprecision with the response. Over on the right, you've got random response. So this is to assume that people are completely random. So whatever presented angle, people will report whatever angle. And that should form just a clear uniform sheet across the scatter plot. But what's most interesting is the guess band response in the middle. If people are biased to the middle of the quadrants, we should see this line, these horizontal lines across the scatter plot exactly at the middle of these quadrants. So for example, for the first experiment, it should be at 45, 135, 225, and 315. Okay, so these are the results. This is experiment 1 with no backgrounds. And you can see we reproduced the error distributions that Kirsten had shown in her early study, where we see a central tendency in the first 3 responses, but in the 4th, 5th, and 6th responses, we see something with some bumps. It may be flat, it may not be. However, we look at the scatter plots, we do see the diagonal component very clearly in the first 3 responses, but that diagonal component seems to disappear by the later responses. Now let's have a look at the distributions when we add those quadrant backgrounds. So again, we reproduce the error distributions that we've been looking into as a field. And however, if you look at the scatter plots, we do see the diagonal component for the first 3 responses, but you can see from the perhaps even the second response onwards, you see some sort of horizontal bias. And so you can see these horizontal guess bands. And what's critical about it being horizontal is that no matter what the presented angle was, people are still reporting those middle reported angles. So no matter what was presented, people are still reporting 45, 135, 225, and 315. Of course, this might be an inherent bias. We haven't shown that this is due to the colored quadrant backgrounds, but remember, we rotated the backgrounds 45 degrees. So we should see these guess bands shift 45 degrees with that change. And that's exactly what we saw. This is experiment 2. And again, we see the diagonal component for the first 3 responses, but then towards the later responses, you do see these guess bands again, and now they're at the 0, 90, 180, and 270. So they've been rotated 45 degrees with the colored quadrant backgrounds. Okay, so this is clear visual evidence for guess bands and what we think are guesses that are indicative of the item limit model. So we found the evidence that has sort of plagued the field. We've shown that people respond in a way that doesn't seem to be easily explained by an imprecise memory. So I think typically we would then infer, haha, yes, there must be an item-based capacity limit. Thanks to reviewers, so thanks to Mike Pratt and my co-authors, we were careful in the paper to try not to make that inference. We were very careful to say, hey, this is in line with an item-based capacity limit, but a resource limit can also capture this kind of empirical pattern as well. Simply, the resource model would include some ad hoc change where you would incorporate priors into the distributions. So, for example, if you have a prior to respond to the middle of the quadrants, and you don't have much of a memory for it, then you would respond based according to your priors. So while there may be a working memory in that distribution somewhere, if you multiply it by the prior, it just doesn't come out. You can't see it. You get the biased response, or the response based on the expectations, the priors. So we were careful to say a resource model can explain the data as well as an item limit model. We're careful not to try to binarize the situation and say, we have shown the evidence and shown the standard for item limit models being correct. All right, so moving on to the next empirical findings. This is what I've called conjunction whole report, and this is work with Christian Loetscher and Edo. So in this paradigm, we did whole report just like we did previously, as I've shown you. However, this time, these are the first whole report experiments that I'm aware of that use conjunction stimuli. So stimuli from multiple feature dimensions. And we use the response interface that collects both features with one click, inspired by work from Kei Fukuda's lab from Sony et al. 2021. So this is what it looks like. So participants are shown colored clock faces, and they have to remember the color and the orientation. And what's neat about the response interface is when participants click in the location, they can drag their mouse to a specific radius to respond to the color, but in a specific direction at the same time to report the angle. So they can respond to both feature dimensions with one click, which helps us get away from some serial order issues or some interference issues. Again, it's whole report, so participants have to report or respond to all items in the display before moving on to the next trial. And what they've reported remains on the screen. Okay. So again, going back to this debate from before, this slot versus resources debate, another branch or an arm of that debate has been whether the unit of visual working memory is objects or features. I'm sure you've heard this in some way before as well. So we've kind of got a situation where we have object-based theories and feature-based theories. So imagine I'm showing you these colored triangles, and you have to remember the color and the angle of these isosceles triangles. So let's take a very specific object-based model, and let's call it the strong objects model. And in this model, it assumes that we have a fixed capacity limit, like I've shown you previously, but that the representations are lossless. So they're all or none memories. And this has been assumed because the addition of features to the stimulus should have no impact because it's just purely object-based. So there should be no impact of complexity on your memory for these objects. Here's how I'm going to show you the data. So on the y-axis is proportion of trials, and there's sort of 4 possible types of responses that can be made. The first is that you could respond to both features correctly. So you can both get the color and the angle correct. You could also drop the angle and get only the color correct, or you can drop the color and only get orientation correct, or you could get both features incorrect. So those are the 4 possible types of responses that you can make. And what we're going to do is we're going to see those responses ordered from 1 to 6, from first to sixth response in the whole report trial. So if we take the strong objects model, we assume that people remember, let's say, 3 objects if the item limit is 3. And so you would remember those lossless and perfectly. So there's perfect recall within that limit, you get both features correct. Beyond that item limit, we'd get the guessing. So we'd expect people to guess from the remaining colors that they haven't guessed from, and it would look something like this. Okay. Now we could also do the same thing with a resource model. Let's call it the independent features model. Here, working memory resources are distributed to all items in the array, just like I showed you earlier, the variable precision model. But what's key here is that feature storage is not constrained by which objects contain the features. Objecthood doesn't matter here. So whether an object is successfully stored is the probability is independent to what object it belongs to. And this should leave us with a whole gamut of responses. You should sometimes remember the color and the angle. You should sometimes remember the color and the shape, but not the angle. Sometimes you might remember just the angle and not the color. Sometimes you might remember the shape and the angle and not the color, whatever. So you can remember all sorts of responses, but that is because the resources are distributed across all the items in the array without respect to its objecthood. So if I show you the predicted result, what we should see is accurate recall distributed across all the responses and all types of kinds of responses across all 6 responses. So you can see sometimes you get both features correct, sometimes you get just a feature correct or just the orientation correct. And because there's no objecthood, they're independent, we should see that responses distributed across the entire display, across all 6 responses. Okay. Now, the enduring theoretical framework for a long time, and I think still shapes our thinking, is this sort of slots versus resources, objects versus features, right? But however, there is an alternative to this, which is simply denying that these models are binary in a way. So our new model characterization is what we've been calling the pointer model. Simply put, you have object-based pointers that points to the features of each object. So it points to, for example, the location, the shape, the color, or the angle. However, this pointing isn't always perfect. You might have weak memories for certain features. You might also have no memory for certain features because you failed to bind those features to this pointer. And that predicts a certain type of response. Here, we still maintain an item limit. It's just that the accurate recall is constrained within that item limit, except it's no longer lossless. So you can have independent forgetting of the features, let's say. So sometimes you remember both features correct, but sometimes you also just report one of the features correct too in that item limit. However, beyond that item limit, again, you should guess from the remaining colors you haven't selected. So you just guess beyond the item limit. And that would predict the same kind of distribution for the later responses. Okay. So this is what we did. These are conjunction Hall report experiments. We had 4 experiments, each with 30 subjects. These were multi-session studies. Each subject took about 5 hours to collect 5 hours of data collection. So because they did 300 trials each of 3 conditions. The 3 conditions are the single feature conditions, so color only, or orientation only, or shape only, or the conjunction condition. So 3 conditions where they did 300 trials each of Hall report. And there were 4 experiments, colored clock faces, as I've shown you, colored clock faces but rapid, which is at 150 millisecond presentation rather than 500. Colored triangles, which is another stimulus that the field has used to look at color and orientation, and colored shapes. So we could generalize from color and angle to also another feature dimension. I also want to point out that the colors, orientations, and shapes here were discrete. It wasn't continuous. Okay, so here are the results. So the recall accuracy for the single feature conditions hovered around 3, maybe a little bit above 3 for colors, and a little bit below 3 for orientations, and also a little bit above 3 for shapes. Notably, we made sure the shapes were extremely dissimilar, so they could be easily discriminated. So that's perhaps inflating these recall accuracy measures. But what's clear here is when we look at how many conjunctions people remember, they don't remember the same number of conjunctions. They don't remember 3 conjunctions, say, in any of the experiments. So the memory for the conjunction stimuli is not lossless. There are fewer conjunctions recorded overall. And people have argued it's because they've observed this, it's not objects. The unit of visual working memory must not be objects. It must be features, because we see an effect of complexity, an effect of an additional number of features. However, if we look at the number of features recorded in those conjunction conditions, we see people record maybe 5 or so features in that display. So they're recording more information than they did in the single feature condition. So it doesn't seem to be a feature-based information limit. This has been previously observed. This is known as an object-based benefit. When you organize your memories in terms of objects, you remember more information. And so more features are recorded overall in the conjunction condition. And people have pointed at this and said, I've shown an object-based benefit. The unit of working memory must therefore be objects and not features. However, what's key in this design is we saw both. We saw both a feature-based effect and an object-based effect happening at the same time in concert. So it can't be one or the other. It must be something to do with both. Now I'm going to show you the data across the responses like I explained earlier. And what's key here is that the empirical pattern was replicated across all 4 experiments. It's a little bit crowded, so let me zoom into the first and the 4th experiment. You can see this is the empirical pattern here. What we see is people on the first response are certainly get both features correct most of the time. And on the second response, also still getting both features correct. On the third response, they are still getting both features correct better than chance. But by the fourth, fifth, and sixth response, it appears that people are starting to guess. The responses look exactly the same. And so I'm going to let you look at the empirical data on the top and the model predictions on the bottom, and let your eyes scan up and down. And hopefully what you can see is that the pointer model seems to match the data way better than all the other models. So a model that takes ideas from the object-based theories and the feature-based theories together seem to provide a good integrative explanation for the empirical data that we observed. And so of note, this pointer model wasn't something that we initially conceived of ourselves. It's actually inspired by other work. So pointers are a good mechanism to maintain on understanding how we maintain representations of objects through changes in its features. So for example, Polishin in 1989, who designed the multiple object tracking paradigm, talks about fingers of instantiation, where you can place fingers on the screen and track their objects so that you know it's the same object moving and changing, and allows us to index what those objects are. Also, Kahneman et al. In their theories of visual attention talk about object files and allowing for an idea of object-based attention rather than purely feature-based attention. And so the key, what I wanted to share from this empirical finding is that we don't think that working memory is simply objects or simply features. We're seeing both sets of phenomena in concert. So perhaps our models should account for both sets of features in a sort of pointer-based way. So just to recap, what have we learned? In guess bands, we did find clear evidence for guessing that is in line with the discrete item-limit model, but we're careful to say, no, a continuous resource model can also account for the data with an inclusion of priors. And with conjunction Hall report, we saw object-based and feature-based phenomena in concert. So working memory is likely not objects or features. It's likely to be somewhere in between. Okay, so now we have established that probably it's not within these binary models, it's somewhere in the middle. How do we address this? How do we address the theory crisis? And can we bring these models into accordance somehow? So I like the approach that's proposed by Bernard Deversier in a lot of her work, where she suggests we need to move away from dualistic experiments and a sort of a results-oriented scientist towards a more model-centric science. And we simply need more theory development. We need to be repeating and detailing the phenomena that we hope to explain. We need to integrate various empirical results and models. We need to clearly specify our theories and models and how they connect to the phenomena that we're trying to research and understand. We need to be careful about generalizing our current models. We need better thought out methods and measures. And we need to rigorously design experiments to truly test hypotheses. It sounds like a lot, but I think about the parable where we have three blind men feeling around an elephant. One is feeling the tusk, one is feeling the leg, one is feeling the tail. And in that parable, they can't agree on what an elephant looks like because they are feeling separate parts of the elephant. What we need is repeated measures, repeated feeling around, and integration between each of these ideas to hone in on our concept of an elephant, or in this case, hone in our concept of a working memory system. So that was the inspiration behind what I call a theory map. So my idea was that we need something like a world map, something that allows us to navigate the landscape. Simply, it's now the landscape of our theoretical frameworks. So rather than introduce a new model and trying to introduce like a whole mind map of what's going on in the field, I thought it was better to try and seek out the existing model that could explain and encompass a wide range of phenomena. And I settled on Brad Weibel's memory for latent representations model. The idea here is that you can map different phenomena and indeed different models onto the same space and that allows you to compare and contrast these models. And also shows that these models aren't necessarily mutually exclusive. They can all just be explaining different parts of our working memory system. So let me go into this model a little bit more detail. So the bow tie shape, you can think of that as a perceptual brain. In computational terms, it's a variational autoencoder. It has multiple layers, and it's kind of like having a V1 a V4 and an IT, like the human brain, and then it's symmetrically back out. So IT, V4, V1 to output the perception. So it's receiving, it's kind of like a perceptual brain. It's receiving inputs into these layers, and these multiple layers then feed into what is known as a binding pool. What's key here is those initial layers, like the IT, include a space for feature maps. So you can have independent feature layers, like, for example, an independent feature or independent layer for color, independent layer for shape, for example, and they can have different influences on what is represented in working memory. The working memory part is the binding pool, and that's inspired by population coding. The idea here is those weights or those inputs from the early perceptual layers feed into a pool of working memory neurons, and they produce a specific pattern of activity. And so that specific pattern of activity is stored and remembered, and then can be pushed back into the perceptual brain for eventual behavioral output. And this binding pool is captured very well by things like neural population models or signal detection accounts. And the main sort of theoretical thrust there is that this pattern of activity is likely to be noisy. There's likely to be a noisy representation in this binding pool of neurons. Now, we need also a mechanism to hold specific patterns of activity, perhaps multiple patterns of activity that are specific. So in that model, Brad Weibel uses tokens, but we call them pointers. I think they're very similar things. The idea here is that you need to store that specific pattern of activity in a separate place to allow other inputs or allow other working memories. But then you can retrieve that specific pattern of activity by tapping into those tokens and generating that activity in the binding pool and then back into the perceptual brain. And so you can start to imagine certain effects like distortion or bias from incoming perceptual inputs, as this binding pool is a common space for working memory. And we think this is a good mechanism for storing memories because we have in our lab shown and found a multivariate load signature that seems to index the load signal. So that seems to index the amount of tokens that we're applying or the amount of pointers we're assigning in working memory. And that seems to generalize across different feature content. So this is kind of new because I think this is a different conception of what attention is and a different conception of working memory. These tokens are a result of a bunch of feature binding and a lot of inputs and a lot of things going in. So it appears that working memory may be a very late stage of encoding and selection. And I don't think people have been thinking about working memory in that way or thinking about working memory as a really late stage attention filter or attention gate. This is integrative. This is in line with other people's work on attention, such as Alon Zavoni's diachronic theory of visual attention, as well as Blair Dubé's dual theory of attention that she actually presented in this seminar a while ago. So I think that these are in line with those ideas as well. So again, if you accept that if you accept this theory map is somewhat accurate, you might realize that there are the empirical phenomena that we attach to working memory, for example, capacity limits, biases in representation, retro cue effects, can occur at any of these levels. You can have any level effect or impact the output or the phenomena that we see. And also these models that we have pit against each other, for example, slots versus resources, or object versus features aren't actually, don't reflect the reality. They're actually probably not mutually exclusive. You can have sort of both at the same time. So we need to be careful about what inferences we make about the model. And also, hopefully, I want to be sure to be clear to say that I don't think this map is right. This map is probably not accurate. In fact, I'd love to hear that I'm wrong. You probably have your own ideas about what this map and what this model might be. You might not like certain attachment of certain phenomena to specific levels. You might not like that. You might not even agree with the existence of tokens. And that's all fine. But now we have a common space where we can actually discuss and be specific about what we're arguing about or what we're talking about when we mean working memory, for example. Okay, so the goal for my theory map, if I'm lucky enough for the field to accept that these ideas are probably good, I think it provides the field a common core language and framework to discuss these models and also to reveal maybe hidden intuitions that people might have or hidden perspectives. I think it prevents misunderstandings from having the varying definitions that I pointed out earlier. It better specifies the connection between specific models and phenomena. It reduces straw manning of various positions, and it discourages this dualistic framework for designing experiments. And hopefully then we can better design models, model comparisons, or better design severe empirical tests to actually distinguish what we're looking at in the working memory system. I'm a big fan of Paul Feyerabend, who's a philosopher of science. He inspires me a lot, and he raises this idea of counter-induction. The idea is you should be strengthening all the other models. You should be developing the other models in what is otherwise known as steelman. Steelmanning those models to show that perhaps your pet model is correct, because rather than showing that your model can defeat a weak model, you should be showing that your model outcompetes a strong model. There's the classic toothbrushes. Models are like toothbrushes. No one likes to use someone else's. We should try and curb that. We should be more pluralistic and understand what everyone else's models are trying to get at, and maybe try and integrate those ideas into a supermodel. And I think if we think about that a bit more, it should stop people and slow people down from defining empirical tests or rushing into an empirical test. It encourages sort of a slower science from better thought out studies. And the reason that's important is, again, as I started this talk with, we're increasing the number of publications and we are under capitalistic pressures to produce. And perhaps we're not making the progress that we want to. And this is perhaps not indicative of the scientific progress we can achieve. So I just want to say, like, feeding that capitalistic academic system devalues your work. We're pushing ourselves into a tension economy that doesn't integrate and doesn't allow us to understand and take each other's perspectives and to take on this pluralistic approach to science. So slow down and think again and test carefully. So my main message is think carefully about how the theories connect to your tests. Remember that memory is multifaceted. And if you do want to think about visual working memory, maybe my theory map can help. Of course, I'd love to hear your thoughts and ideas. Feel free to email me, because one way to better understanding in science is to simply have more conversations and discussions. So please feel free to email me. So that's all I have for this talk.